Okay, in this video we're just going to look at how to spot chiral sensors. Okay, first of all, the definitions from page 2 of your booklets. You'll see stereoisomers, species with the same structural formula but with a different arrangement of atoms in space. You've seen that previously with alkenes, EZ isomers of alkenes. Some new definitions. A chiral carbon, so it's a carbon which has got 4 different groups or atoms attached to it. And then optical isomers and enantiomers, these two terms are used interchangeably, they mean the same thing, which is that these are stereoisomers that are non-superimposable images of each other. So this means the stereoisomers because they have got 4 different groups attached to a carbon, and then you've got 2 versions which do not overlay each other, which we'll see on the next page. Okay, so here we've got a chiral carbon in the center here. We've got a bromine, a hydrogen, a methyl, and an ethyl group attached to it. We have got 4 different groups. That's why it's chiral. This molecule here is has also got a bromine, a hydrogen, a methyl, and an ethyl group attached to it. This molecule, if you were to pick it up and put it on top of this molecule, you would see that the ethyl and the hydrogen groups would be pointing in different directions. So these are non-superimposable images of each other. They are mirror images of each other. Okay, so let's just go through a few examples of trying to spot some chiral sensors. Here we've got 2,3-dimethyl butane. If you look, the end carbons, they've got 3 hydrogens, so there's definitely no 4 different groups there. And then on carbon number 2 and also on carbon number 3, you've got 2 methyl groups, so there is no chiral carbon there. For the 2-bromo-propanoic acid, we have got on carbon number 2, we've got a bromine, a hydrogen, a methyl, then a carboxylic acid functional group. So we've got 4 different groups here, so that carbon is chiral. If we look at this molecule here, you've got 2 methyl groups, a nitrile and an OH, so that just means because you've got the 2 methyl groups, it is a non-chiral carbon. These skeletal diagrams are sometimes more difficult to spot what's going on. So if we start with this molecule here, remember in a skeletal diagram you do not show your carbon-hydrogen bond, so this is not a true skeletal diagram because I'm showing my carbon-hydrogen here in my aldehyde. So this carbon down here, it's got this part of the cyclohexane ring, it's got this alkyl going to an alcohol, and this carbon here is different to this carbon here because it's got this aldehyde group attached to it. So this has got a chiral center here. If you go through the same process, you'll see there's a hydrogen missing there. There's a hydrogen there that is not shown. An aldehyde, you've got a CH2 and a CH with an alkyl group off it. So this carbon and this carbon are different, so therefore we have another chiral center. Methyl cyclopentane, slightly different because you've got this methyl group here, a hydrogen is not being shown, but this CH2 and this CH2 are equivalent because they're both attached to another CH2 and another CH2. So that is not a chiral center. Similarly for 2-bromopropane and for the methyl butane here. This molecule here, 1, 2, 3, 4, 5, it is 3-hydroxy pentanoic acid. This carbon here has got a hydrogen attached to it, which isn't shown, an ethyl group, an OH, and this other group with a carboxylic acid on it. Therefore, this does have 4 different groups, so this is a chiral carbon. Finally, just as a quick reminder, these alkenes, they are EZ isomers, they are stereoisomers, but they are not optical isomers. Okay, so don't get confused between the two. You may be asked to identify if a product from a reaction is chiral or it's not chiral, but again, you'll go through the same process. You look at each carbon in turn in the product and decide if it has 4 different groups attached to it. So you'll see that this product is not chiral, this product is chiral, and this product is chiral too. Finally, the big molecule here. Nature is very good at making complicated molecules with lots of these chiral carbons in them. This is Taxol, which is an anti-cancer treatment. So let's just go through the molecules, see how many chiral centers we can find. We can see 1 center here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There is not a chiral center here because you've got 2 methyl groups which are the same. You don't have a chiral center here because you've got a carbon-carbon double bond similarly here. Okay, so that's sometimes the exams have to run up complicated structures similar to this, and they've asked you to identify the number of chiral carbons. So hopefully this has helped. Okay, thanks for watching.